Welcome back. And we're going to do the retro from winter 18, test 3. And to do so, we need to look at this. We're going to do a retrosynthetic analysis for the target molecule here that ends in saturated alcohols of 5 carbons or less, benzene and D-ribose. Wow, D-ribose. What's D-ribose give us? Oh, a useful reaction says D-ribose can be dehydrated. How many waters got lost here? Carbonyl, alpha no has the O. Okay, kept that O. Lost this water, lost this water, lost this water. 3 waters. Not that that's important. But the fact is you have this furan ring here with an aldehyde. It's called Furferal. So this piece of the molecule, every time we see these carbons in our target, they came from Furferal. So I have the same 4 carbons. Oh, that's 5 carbons, isn't it? Let's make sure we circled 5 carbons. That comes from Furferal. And careful, only that comes from Furferal. We got to extend it by 1 carbon there. We did that on our first test, extending things by 1 carbon. We have an iodine. So hints for studying. Okay, one of the groups on your retro for your test. One group. Sorry, I'm kind of leaning here. I was grading all weekend and moved things back. Here we go. For your test 1 group will be primary alkyl. Put a little red check mark. I'm talking about the 3 groups on benzene here, right? You do know it's going to be 3 groups on benzene, right? This is about the 4th time we've talked about it. 1 will be primary alkyl. 1 will be from a diazonium ion. B, 1BB from a diazonium protocol. How's that? Sounds fancier that way. We'll put a purple check mark there. The only way we learned how to put iodine on there was from a diazonium. 1 will be. That is a big eraser. Purple will. Okay. Let's roll. Primary groups. This should be of primary interest to you. Pun intended. The primary group, after you get it on there, is an ortho-para director. So you ask yourself, do I have another group in this molecule, ortho or para to this? And the answer is yes, I have a para here. So I can take advantage of this being a primary group to put this group on, okay, more towards the end of the synthesis. Then you got to remember what we just talked about in our first segment. You can't put a primary carbon group directly on benzene. This carbon here used to be a carbonyl, and I got good news about that too. A carbonyl is a meta-director. So, in review, you're going to be putting a carbonyl version of this group on benzene. I suggest you do that first. You know what you do second? The diazonium protocol. First, get the nitrogen on there, reduce it down, and do the diazonium reaction. And after you're finished with that, reduce this to a CH2. Okay? After you've reduced that to a CH2, you're going to have a CH2 on the same molecule as an iodine. Which one's more important? Well, a CH2 with its hyperconjugation abilities is more important than any halogen with a lone pair. So this will take over and direct towards the para position. So once again, I don't even pretend to start with the retro, and these, you don't have to either. I start with the forward synthesis after I did my discussion with myself right now. So broad strokes, I'm leaving a little room because I probably have to make some stuff that goes on here. I need to make this group first. And I don't want to ever draw that ring. And I better circle it because right now I don't have anything with an R. Yeah. R is just the ring. Pink. I have all the rings circled. There. And how do you do that? Quite simply, you put a Cl, carbonyl, CH2R. And we're going to have to make that species. Now, this will only get you partial credit. Putting a group on benzene requires a Lewis acid of the aluminum variety. Aluminum chloride. There you go. So we still have to make the pink thing. Now I have to take advantage of the fact that this is a meta director and my target has a group meta to that position. And I need to put, how do you get an iodine on there? That was like 3 steps. I'll remind you, you got to put a nitro on first and then reduce it to an amino. I'll put this in a square thing here. Or maybe not. R. And how do you do that? Nitro first. HNO3, H2SO4. And then I got to reduce that without reducing my ketone. Be very careful here. Don't use lithium aluminum hydride. It will reduce your ketone to an alcohol, and I don't want that. Let's do the old Clemenson. Zinc amalgam. Alloys of mercury are called amalgams. And HCl. Get your NH2 up there. And then the diazotization protocol goes like this. Part 1. Make that into an N-triple-N with a plus charge called a diazonium ion using these sets of chemicals and these conditions. Don't try to skip any of these parts. 0 degrees is important or else you get a phenol up there. And part 2, how do you convert a diazonium ion to an iodine? And that was one of the easier ones. Potassium iodide. And what's RT stand for? No, not Russian television. Room temperature. And you have your iodine on there. We're wandering over towards our target molecule, by the way. 2 groups on benzene. Now my next group would go somewhere where I don't want. If I tried to put a new group on benzene now using electrophilic aromatic substitution, let's see, I got an ortho para director that's more important than a meta director. Next group's probably going to go here and a little bit here, maybe 50-50. Who knows?
Professor,
Yeah,
we reduced the ketone already.
I
So we
did.
just should have CH2. Right?
Yeah, that solves this whole question I've been talking about. Thank you. Yeah, I forgot how I did some steps today. Said I was going to do. Let's just fix that. Yeah, it's a CH2 in the second step there. Yeah, thank you. But now I'll continue that same discussion. I have a more important R group. Let's just get rid of the whole thing. CH2, CH2R. That's more important than an iodine. So the next group will go in our desired position here. The question is, how the heck do I get a CH2 group with an oxygen attached? You got options. Got options. I don't think I can bring this whole thing in. How about a CH3 group that I could put a bromine on later and do like an ether synthesis? How's that? What's important about a CH3 group attached to benzene? It's called benzylic. And then it's easy to put a halogen there. But then again, it's also easy to put a halogen here, the same protocol. So I got problems. I'm wondering. Can I bring a carbon here that's a carbonyl? Carbonyl, that could be done with a leaving group on it as well. Just thinking out loud here. Thinking out loud. I could put a cyanide on here and do hydrolysis to a carboxylic acid and reduce it. That's a thing. Do you want to do that? It'll be different than the key, I'm pretty sure. And it helps us review our protocols. Let me just see if you can figure out what I'm doing here. 1, HNO3, doing it again, HNO3, H2SO4. I'd like to remind you that reaction generally requires a little heat. You don't have to put the heat. In fact, I'll leave it off. There. So you're going to put a nitro group here as your major product, para to the ortho para director, also ortho to this group. And then I'm going to reduce it down to an NH2 again. I can use my same chemicals. I used zinc amalgam. Wait a minute, that's not for NO2. That was for carbonyl. Where did I reduce my nitro group? Oh, that was for reducing here. I have a nitro group still on top. I didn't do step 3 here. There's lots of flaws in this thing. You can't do the diazonium ion until you have the NH2 up here. I have an NO2 after step 2. This only touched the carbonyl. So how do I reduce? And I erased a lot of things. Didn't fix them. Shame on me. So we've taken care of that business. So I can use any method to now reduce my nitro to an NH2. I can use step 3, lithium aluminum hydride, followed by step 4, HCl. And now I have my NH2. Similarly here, I can use lithium aluminum hydride, followed by HCl. And what do I have now? I have an NH2 group right here. And I'm going to go with the cyanide on there because I know cyanides can be hydrolyzed to carboxylic acids, and then they can be reduced carboxylic acids to alcohols. And then I'll think about a Williamson ether synthesis with an O-. So where are we at now? We're doing nitration reduction, and we have this here. Iodine as required. NH2, which is going to lead us to cyanide. then hydrolysis of cyanide, we'll fill out the chemicals later, gives a CH2O, carboxylic acid. Hydrolysis. I'm running into room I'm going to need later. And let's just keep this rolling up here. And then we're going to go here with stuff we don't have yet. Turned my pen off. There. So good review. How do we go from here to here? You do the diazotization protocol here, followed by not Ki, but KCN and copper CN. So 1 NaNO2 HCl AQ. You don't have to put XS. There you go. That gets me step 1 here, and then step 2 KCN. Whoa. KH, where'd that come from? KCN, CuCN. Don't forget, this step always requires room temperature. And hydrolysis, H2O, H2SO4. Makes sense. Hydrolysis, catalyst, almost always sulfuric acid. Then lithium aluminum hydride reduction, followed by HCl. And then a Williamson ether synthesis with, need something that shows up here. Cl, R, we have to make that. R's our ring. Cl attached to CH2, there's the CH2, there's the R. So, I don't know, we'd have to copy this up here. Here's the fastest way on the test to copy what's up there. You don't have to copy the molecule, but you do have to copy this reaction down. Showing me you know what's going on. And you get R carbonyl. And whether you're going to use this version of it or this version of it, you're going to need redox. Acid halides, how do you make those? How do you make acid halides? One, you oxidize it. CrO3, H2SO4AQ. Got to have the oxidation state of a carboxylic acid before you do your old SOCl2 and pyridine. Now the question is, where does your ClR come from? And you've got to reduce it to an alcohol. So number 1, you can use NaBH4. And 2 HCl. So you got an alcohol, and then how do you make the alcohol into a chloro compound, alkyl chloride, SOCl2? Ugh. Whoa. SOCl2 pyridine. And this arrow is no longer my retro arrow. So the retro arrows go like this now. This is where you pretend, oh, I was doing retro all along, Dr. Whitaker, didn't you notice? This came from that. And where'd that come from? Well, that came from that. And this came from this. And let's get artistic here, which for me is always dangerous. Don't have that ability. And that came from that. And this came from this. And this came from this. It's actually stress relieving. And this came from that. We can go here. Oops, don't write over the O if you don't have to. And where'd this come from? It came from this. And this came from, oh boy, it's getting tricky. And this CLR, oh boy. This, this came from, this came from this. Below, this is going to be hard. And it crossed. Oh, it's a Möbius retro arrow. I like it. Okay, and of course, D-ribose gave us the aldehyde. Aldehyde came from D-ribose. So this has a little more than yours will have. This was a bit of a thinker, this one. Yours will be a little more straightforward. I hope that gives you a little solace. So any questions on that one? Let's just take a look at what we're doing next. And it looks like I had a student request the bonus mechanism on 2 different occasions. I'm not going to do that one, and you won't have that bonus. And they selected this one. I think they selected it because it had these things, but I'm going to cross them off. We did not cover silicon protection. So what I'm going to do on the next page, I think there's a continuation here. I'm not 100% sure about that. Is there a continuation? There's a continuation. So I don't even know if we're going to do that. We could start here, in which case it's just a review reaction. It's worth doing. But anything with the silicon protecting groups, either taking them off here or putting them on over here, putting them on over here, you're not responsible for that. Although we should be able to do this. So after break, we're going to do that, that, and that, followed by that. And I'll see you then. How are we doing on time? Pretty good. And stopping.